Piggy and Pixie are the fun names for what's called proton-induced X-ray and gamma emission. So that's when we have a proton beam and we basically direct that beam onto any sort of material. And the way that that proton beam interacts with the material gives off gamma rays or X-rays. And those are characteristic of particular elements. So we can use that and we can detect things such as fluorine, we can detect lead, and we can detect most elements in the periodic table.
The St. George recoil mass separator is one of the 4 recoil mass separators that existed on the world to help us to study and isolate the interested radioactive nuclei or recoils from nuclear reactions that we make in our laboratory. That allow us to probe and trying to figure out where some of the elements are made in our universe.
So ICEBAL stands for the Internal Conversion Electron Ball Array. It is a setup that's used to detect electrons that are emitted from nuclear reactions. There are certain transitions between the different excited states where you only see the electron get emitted and nothing else. But detecting these electrons is much easier said than done. That's what we're hoping to achieve with my project here, being able to detect those electrons easier.
RHINO, which is short for rhinoceros, is a windowless gas target system which allows us to take high-intensity beams from the 5U accelerator and measure low-probability reactions which have astrophysical impacts.
So AMS is an acronym for Accelerator Mass Spectrometry, and essentially it is a technique that allows us to measure very low concentrations of long-lived radioisotopes. We're looking at those very low concentrations because the existence of these long-lived radioisotopes can tell us a wide variety of things. We've got carbon-14 existing, which we can use to date any sort of organic specimen. We've got chlorine-36 and calcium-41, which we can use to look at early solar system formation models and constrain those models.
So HECTOR is a total absorption spectrometer, and that means that it is really good at measuring gamma rays from reactions. And the reactions that we measure with HECTOR are called radiative capture reactions. And that's where your target nucleus absorbs either a proton or an alpha particle, for instance, and emits gamma rays. And so we measure the gamma rays that are emitted in that reaction, and we can figure out from there how often that reaction occurred.
A lot of nuclei in the universe that we want to study, involving how stars form and how they produce heavier elements, involve studying nuclei that aren't always stable. So one of the ways that we do this in nuclear physics is we make a beam of these radioactive particles. So what TwinSol does, and has been doing for the last few decades, is makes these radioactive beams. And they use them for a variety of measurements depending on what the situation is. One of the things we've been developing in the last year or so is called TriSol. So we added a switching magnet, a third solenoid, and a set of analyzing slits. And that would allow us to better focus our radioactive beams that we make and to purify them to a higher degree. Next to TriSol, we're building what we call the St. Benedict trap. It's the super allowed transition beta neutrino decay ion coincidence trap. So what St. Benedict is going to do is going to capture TwinSol beams, not TriSol, but TwinSol beams, purify them, collect them in these little bunches, and then it'll magnetically hold them in this vacuum chamber. And when they beta decay, you'll get a positron going one way, and the heavy recoil will go the opposite direction. We'll measure the angle and energy of both of those particles very precisely, and from that we can extrapolate where the neutrino went, which is the information we actually want. The ND Cube is a time projection chamber that Professor Ahn, who works in the nuclear lab with us, has been developing for the last few years. A time projection chamber is like an ionization chamber that reconstructs events. It's what we call a thick target detector. So beam will come in and ultimately stop. But because we're tracking it as it's traveling through, we will know at what exact point an event happens. And particularly, he's studying fusion barriers. So he's looking for a fusion event to occur, and then he can tell at what point that is, so he knows at what energy that event occurred. That gives him some interesting information about the study of nuclear structure and things like that.
The Institute for Structure and Nuclear Astrophysics, as it is now called, celebrated 80 years of nuclear physics study at Notre Dame. We would not be where we are today without the support of our students, as well as the incredible trust and financial support from the University of Notre Dame and the United States National Science Foundation.